So hello everyone, this is lecture 12 for the quantum mechanics. In the last lecture we were discussing about the normalization, and we were discussing about the how we say that if some wave function is valid or not. Okay, so we were seeing the Bond's interpretation. So today we will see our wave function in some position space, momentum space. So let's see. So we already described our wave function in terms of Fourier series. We already told you that we can write our wave function in this form if our k is continuous and particle is free. So if it is free particle, then what is the meaning of free particle? Means there is no force acting on it. Okay, it's just moving freely. So for free particle we can write wave function in this form: 1 upon root 2 by minus infinity to infinity. This is phi k exponential I k x dk. So I already told you how to find this expression. Okay, so if this is your any particle, then you can write wave packet for this is this wave, and this is nothing but probability wave, and this is wave packet. That's how you describe your particle in the waveform. And this waveform or wave packet is form of a large number of continuous waves. So means k is continuous here, minus infinity to infinity, so it will give you an infinite number of waves. Then superposition of all these waves will give you this wave function that is here. Means this is your phi k, and this is the amplitude of each single waves. So phi 1 can be written in this form: some amplitude exponential I kx, phi 2 will be exponential I k2x. Then sum of these all phi and exponential I kx will give you your wave function. Okay, because this is a superpositions, means when you add all of them, then you will get your wave function. Okay, so superimposing all of them, all of the waves will give you this wave function. That's how we can write this expression. Okay, now you have wave function. Now you can describe this wave function in position space and momentum space. So what is the meaning of the position space or momentum space? So when you describe your wave function here and you have the x-axis time, the position, then you say that it is in the position space. But when you have your wave function in terms of momentum, means on x-axis you have momentum and here you have your wave function, then that is called your momentum space. Okay, so let's see. In the position space you can define your wave function in this form, because here you can see when you integrate this thing, this phi k or this anything, then in the final you will put these limits in terms of k, then that will give you your this whole value in terms of x. Means k will be removed or eliminated because you will put the limits. So this whole wave whole function will came out to be in the form of x. So that's how you can say that phi x is function of x. So this is in the position space. Okay, now again in the position space itself you can write this whole function in terms of momentum. Means in the position space you can write this whole function in different form, because you know p equal to h cut k, you know this formula. From here you can write k equal to p upon h cut. So after substituting in place of this, it is p upon h cut. So you can write in position space in terms of momentum, because k and p are just a similarity of these other, means they are just related and have the same properties. Okay, so here you can write if p equal to h cut k, then dp will be h cut dk. So in place of dk it will be dp by h cut. So it will be dp by h cut. Now you will write h cut into under root h cut, under root h cut. So 1 under root h cut will go with under root 2 pi, and 1 under root h cut will go with the phi k. In place of k you will write p by h cut. So it will be like this. Now you can write this whole term as in the function of p, because k and p are related, that's why you can write this thing. Now you have in the position space wave function in terms of momentum. So it is in the position space, not the momentum space. We are discussing only the position space now. So this is your wave function in terms of momentum, and you can, this is the same thing as you have this in terms of k, because k and p are related. Now let's see the in the momentum space what happened to wave function in the momentum space. Now we already know we can find the Fourier transform of this function, then we get phi k in terms of phi x. So this relation will be reversed and you will get this thing: phi k equal to 1 upon root 2 pi psi x exponential minus I kx dx. This is nothing but Fourier transform of psi x, that will give you phi k. Now this is depending on k, and k is momentum, means these are same things. So k is depending on momentum and momentum is depending on k. So when you get some function in terms of k, means you are getting in terms of momentum. So this is in the momentum space. Now this is in the k space. You can write this because now you can see if you integrate this function, then you will put the limit for x now, and you will solve this, then you will get your final answer in terms of k. So this is depending on k, means on x-axis you will have k, and in the here you will have phi k. So that's why we are saying that this is a wave function in the k space. And you can write in terms of momentum, you know this relation k equal to p by h cut. So in place of k we can write p by h cut, and here also it will be in terms of p then. So it is just the same thing as we solved here. So this is in your momentum space, the wave function. So that's how you can define these things. So many times question asked in these types of relations. So what kind of questions are asked? Let me tell you. The wave function of a particle in position space is defined as. So wave function is given, in position space is given. Now where a is constant, k naught is positive real constant, we need to find the wave function in p space. So how can you find this in the momentum space? So you know the formula. In momentum space, phi p equal to wave function will be this. Now you will just substitute the value of psi x and you will solve this in the momentum space. So we'll do the same. The psi x is given, so we'll just substitute in place of this psi, we'll substitute this, and everything is same from this formula. Everything is same. Now we just need to solve this integral to find the wave function, because that will be your wave function in momentum space. Now to solve this, we have a very interesting thing here. Now see, we can write this exponential, they will be added, so it will be in this form. Means it will be in I k naught h cut minus p x divided by h cut. Now we'll multiply with 2 pi here and 2 pi here. So why we did this? Why we did this? See, you know about delta function. What is delta function? You can see my complete lecture on delta function in the mathematical physics. You are getting the I button over above. You can see the whole lecture on delta function. You must know about the delta function to know the means in the quantum mechanics there is a very big amount of, or the large amount of applications on based on delta function. So you must know about the delta function. You can see my lecture in the mathematical physics. So what is the use of here? So in delta function we can write in the exponential terms. So delta function can be defined in this form, in the exponential form. Means if this is your given exponential 2 pi iota p2 minus p1 x dx, then this whole value will be written, can be written in this form, delta p2 minus p1. So this will be your delta function. So this can be written in this form. Now we need to turn this in this form. So that's why I write it here 2 pi multiplied here, 2 pi multiplied here. So now we are having 2 pi I k naught h cut minus p by 2 pi h cut x dx. So we are having something like this form, but still we are getting this extra 2 pi h cut. So we can make this into single x. How? We will write x upon 2 pi h cut as capital X. Then from here dx will be 2 pi h cut dx. So in place of dx we will write 2 pi h cut dx. Then you will get 2 pi h cut outside, because under root you have 1 under root, then it will give you under root 2 pi h cut on the numerator. So now you have this form, the same like this. So whatever is here, this will give you delta function inside the delta function. So this will, the value of this thing will be delta k naught h cut minus p. So your wave function in momentum space can be written in this form, a under root 2 pi h cut delta k naught h cut minus p. So this is your answer for this question. But see, you must know about the delta function. Okay, so try to solve these two questions based on the same thing. Wave function of a particle in 1D position is given. So psi x is given, a is constant, k naught is also plus positive constant. We need to find the corresponding wave function in the momentum space and also the possible values of momentum. So you will use the same formula as we used here. In place of psi x you will substitute this value and solve this for momentum. I will give you the answer or the solution in the next lecture, but now you should try. Okay, and try this question also. The wave function of a particle in 1D system is given by psi x equal to a exponential minus alpha mod x, where alpha is positive constant. Find the corresponding normalized wave function in the momentum space. So again you need to find a wave function, then you need to normalize also. So try to solve this. Okay, same as we did here. What you will do here, this is you will separate this into means from minus infinity to infinity you will do minus infinity to 0 and 0 to infinity, because for minus infinity to 0 this will be minus x and 0 to infinity it will be plus x. So that's how you can divide your psi x, then you can solve. So try to solve it, otherwise I will give you a solution definitely in the next lecture. So you will try to solve these questions based on these formulas we discussed. Okay, but as I told you, you must know this delta function. So let's see a brief idea of delta function, otherwise you must see my complete lecture for the more details. So let's see what is this delta function first and how we are getting this thing, means how this is equal to this. So Dirac delta function is nothing but Dirac delta function is 0 everywhere and non-zero at one particular value. So this is the kind of function defined, means if you have something like, means this is only defined on a particular point, then you, so for that reason this Dirac delta function was derived, actually discovered, to describe that kind of things. Means like you have charge density for a charge like electron. Okay, so at a particular point you need to find this density, So it will be, density will be only on that point, otherwise it will be 0. So how to define this kind of function? So that's where we define this Dirac delta function. Mean at only this a point, this will be goes to infinity, otherwise all other points it will be 0. Okay, so to describe this kind of things, they discovered this Dirac delta function. Means it will be 0 everywhere but non-zero at a particular point. So it is defined in this form: delta x will be 0 when x is less than 0, x is greater than 0, but at x equal to 0 it will be infinite. So only it is defined on a single point. Now if this is not 0 and this is at any a point you need to describe, so how you define that at any point a? So you will write in this form: x minus a. So at a it will be infinite, but at all other points x is less than a, x greater than a, this will be 0. Okay, so that's how you describe your Dirac delta function. And sum of this means sum of the area or the integration of this complete delta function will give you always 1. Okay, so integral will always be 1 for Dirac delta function. So that's how we define this Dirac delta function. Now we define in this form, but here I give you Dirac delta function in this form. So why Dirac delta function in this form but not in this form, which is this? Okay, so let's see. So in integral form, Dirac delta function is written in this form. Dirac delta form in integral form is nothing but this in terms of exponential: 1/2 pi minus infinity to infinity exponential ikx dk, and this is in this form. So again this is the function of x and dk is here. See, these x and p are conjugate pairs and e and t are conjugate pairs. So what is the meaning of conjugate pairs? So whenever you plot something, then you can plot in px graph or you can plot in terms of e and t. So that's why we call them conjugate pairs. Okay, so this can be written in p terms also because p and k are related, so you can write this in this form. Same if you have x and p, you can write in terms of e and t also, and e can be written in form of omega, just like you can write k and p related. That's how e and omega can be related. So you can write just like same, you can write for e and t also. So delta e will be 1/2 pi exponential minus iota et dt, and in place of e you can write h cut omega because this is energy of h cut for a wave, that is h cut omega. So you can write this relation for this also. This is the definition of Dirac delta function in terms of exponential. Now what is the meaning of this? So you must know about this. Means you heard in your MSc or BSc that when you study a signal, then like you have your wave function in terms of time here, and you have time in this axis. So you define this wave like this. So this have a particular fixed frequency. Okay, now if you want to find this wave function in terms of frequency, on the x-axis if you define your frequency, then see frequency is constant, so you will get only a single line in this plot. Okay, so this is the same case we are doing here. Means in the momentum space we are describing, so we are just finding the Lorentz transform. So Lorentz transform of psi t will give you psi omega. So we use this thing in the signals. When we study the signals, you will see that it is a Fourier transform of psi t. So you can see my lectures on Fourier transform also. That is a simple thing, means you just convert one variable to another variable. This is not a very big deal. Now see, I told you that you can write your Dirac delta function in this form in the exponential, but how we can say that? Means what is the proof that this is your Dirac delta function? So we must know that this should give you the same values as you are getting here. So this should be defined like this, only then you can say that this is your Dirac delta function. Means when this x tends to particle 0, then you will get infinite value, and other values this must be 0. So let's see the proof. Why this is delta function? So we will take this one. Okay, these are the same, so let's take this one. Now define p by h equal to p, capital P. So dp by h will be equal to capital dp. Now in place of this, see, multiply with 2 pi here, means this h cut is nothing but h by 2 pi. So 2 pi will cancel out, here you will have h only. So dp by h will be equal to dp. So that's how you get dp here. Now this multiply with 2 pi here and 2 pi here, so you will get h upon 2 pi will cancel out, so it will be p upon h, and p upon h is nothing but capital P. So you will get 2 pi I px. So 2 pi I px dp. Now this function can be written in this form by substitution of these things. Now we need to prove that this is your Dirac delta function, means this is infinite at x tends to 0 and 0 at other values. Means now we have taken this limit L to L, then we will take infinity to infinity. Okay, so for that first let's find this function for this limit only. Now see, this is a simple integration. So dp will give you exponential this divided by 2 pi over x, because it is with respect to p. That's why we'll get this thing. Now put the limits plus L to minus L in place of P. So you will get this thing. Now you can separate the 2 iota separately and multiply 1 upon pi x from here. This is nothing but sine. This is exponential I theta minus exponential minus I theta divided by 2i. That is nothing but sine theta. So that's how you can write sine theta here. Now this is pi x in denominator. So theta is here, this 2 pi xl. So that's why you get sine theta divided by pi x. So multiply and divide by 2l here. Then you will get this 2 pi xl here and multiply 2l. So this delta x equal to this. Means this is not proved that this is delta function, but now we are having this function. So this fx is equal to this. We need to prove that this fx is nothing but delta function. So let's prove. So this is your function. Now we need to plot this curve to see if this is your Dirac delta function or not. So what is the plot of sin x divided by x? So we know for sin x by x, for x it tends to 0, this should be 1. So at 0, this should be like 1 here. Then this graph goes like this. So this is the plot of this. So what is the plot of this one? At x tends to 0, this will be 1, so it will be 2l. So value of fx is 2l. So at x tends to 0, this will be 2l. Now this graph should go down and it will be 0 somewhere. So what is the position when this is 0? So this function can be 0 only when this upper numerator can be 0. So sin 2 pi xl should be 0. So 2 pi xl should be n pi. N can be 1, 2, 3, 4. Because if n is 0, then this will again be 0 point. So you can't take n equal to 0. So from here you can find this x equal to n by 2l. So for these points n1 to 3 you will get 0. So first 0 will be n equal to 1. So 1 upon 2l you will get your first 0. Here minus 1 upon 2l, same 2 by 2l, minus 2 by 2l. So that's how you are getting your zeros. Now see, you define this plot here. Now how can we say that this is your Dirac delta function? So for a particular value L, this can't be Dirac delta function, but we need to not need to prove that for L finite value. We need to prove for L tends to infinity, because here we taken infinity as your means when this limit was infinity, only then we said that this is Dirac delta function. So see in this curve first. When this L increases, this curve will go this side. Means as L increases, this will this side, because L is increasing, then this whole term will be decreasing. So this will go this side, and when L increasing, this will go this side. So curve will start to narrow down. So when this is narrowing, then this, as L is increasing, then this point is increasing upside, and this is going this side, this is going this side. So see, when this L tends to infinity, then this value tends to 0. So this will go like here, and this will go like here, and this L tends to infinity, this will go like here. Means it will peak up. It will go to the peak. Okay. So when L tends to infinity, you can see that this is same as the Dirac delta function. It is described or defined only on this point at x equal to 0, and it is 0 at every other place. Okay, because L tends to infinity, this will go give you 0, and here also. So this will go to infinity only on single point. So that's why you can say that this function define your Dirac delta function. So this is your Dirac delta function. Okay, for L tends to infinity. So that's why we can write this function as Dirac delta function x. So we get this definition that Dirac x equal to minus L to L exponential 2 pi iota x p dp. This L should be infinite, means L should be minus infinity to infinity. And you also can see that this area should be 1 according to this definition. This area should be 1. So this is the same function. So you can take the limits. 2l will cancel out. You will take this sine 2 pi xl divided by pi x dx. Then find this area. This will be 1. So try to solve this. Otherwise I will give you the solution in the next lecture. So try to prove this result. So now see, you have this equal to this, and you have two variables. So when you have this p, then here will be dp, and this x, then this Dirac delta function will be defined in terms of x. So see, we use this relation here. Here you can compare these two results. Here you have this x and dx. Here you have p and dp, and whatever is here is coming in the Dirac delta function, and same here, whatever is here is x is coming in the Dirac delta function. So we use this result to solve this, because here you have x dx. Now whatever is here will come in the Dirac delta function. So that's how we define this, or means we solve this question. And this is your Dirac delta function. So you must know all these things. To understand in detail about a Dirac delta function, you must see my lecture. Otherwise this is enough for the quantum mechanics. So thank you everyone. We'll meet you in the next lecture.